Welcome to the Deep Dive, the place where we take those overwhelming stacks of research, the dense articles and the statistical methodologies that really shape our world, and try to turn them into clear, crucial insights. Today, we are wrestling with the invisible, the things we can't touch, but which we assign numbers to, and then we use those numbers to define reality itself.
Yeah, think about it.
How do you measure anxiety? How do you assign a specific objective value to the health of a democracy?
Or even something that feels more concrete, like socioeconomic status.
Exactly. These are concepts that exist, only in theory, these theoretical abstractions we call latent variables.
Right.
Yet we treat them as if they're tangible facts. They form the bedrock of our policies, our medical diagnoses, our psychological profiles, and frankly, our entire self-understanding as a species.
That's the core challenge, really, if you just pause for a moment to consider that nearly all of modern social science, everything from public health to educational theory to psychology, is built on quantifying these unobservable traits.
It's all based on this.
It's all based on this. And so the tool used to do that quantification is, well, it's arguably the most consequential methodological engine ever invented for the human sciences.
And that engine?
That engine is factor analysis, or FA. It's a tool that it forces order onto chaos.
So that's our mission for this deep dive.
That's the mission. We need to dig into the internal structure of this mathematical process. We have to understand its complex underpinnings, how it works, and crucially, where the analyst has to make these subjective decisions.
Okay.
We'll examine its transformative strengths, how it successfully managed to define personality taxonomy, gave us robust measures of social class, and even led to the very concept of general intelligence.
But, and this is the big but.
But crucially, we have to spend significant time on its profound limitations, its capacity for distortion, and the subjective judgments that have fueled some of the most contentious, high-stakes debates in the history of science specifically. That debate around whether intelligence is just a mathematical construct or an immutable biological trait.
Okay, let's unpack this immediately because I think understanding the underlying mechanical premise is everything here.
It is.
So, factor analysis is a multivariate statistical method. Its job is to look at this massive variability among a set of observed correlated variables.
So think of the 50 questions on a personality survey.
Right. Or the 20 indicators used to measure urban health. And it tries to describe that variability in terms of a much smaller number of unobserved variables, which we call the factors.
And the whole thing, the entire operation, rests on a deceptively simple but really powerful philosophical premise.
Which is?
If a bunch of observed things you can see correlate with each other, they must share a common underlying cause.
It's not a coincidence.
It can't be a coincidence. So factor analysis is, at its heart, the statistical modeling of that common cause.
And that premise takes us right into the foundation of the method. If you've ever tried to work with factor analysis in statistical software, you immediately hit the first major conceptual hurdle that just confuses researchers all the time. When should you use factor analysis, FA? And when should you use principal component analysis, or PCA? They look similar, they often give you similar results, and they're frequently mixed up.
And the software often puts them right next to each other, which doesn't help.
Right. But the sources are very, very clear on this.
Right.
They are fundamentally different approaches rooted in totally different scientific goals.
They're not just mathematically distinct, they're theoretically distinct. And, if you are doing social science research, theory development, or clinical scale construction, anything that's focused on truly latent variables, the common factor model, which is FA, is almost always the right choice.
Why is that?
Because it's based on a causal hypothesis.
Okay, what does that mean in practice?
Think of it this way. Factor analysis assumes a specific direction of causality. We call it a reflective model. It assumes that the observed variables, the things people actually check on a survey, like I have trouble sleeping or I feel persistent sadness.
The things you can see.
The things you can see. It assumes those are the effects or the reflections of an underlying unobservable latent cause, which we might label depression.
So the factor, the cause, dictates the responses, which are the effect.
Precisely. The invisible thing, depression, is what causes you to have trouble sleeping. It's not that having trouble sleeping adds up with other things to create depression.
That distinction changes everything, because if I'm just summing up symptom lists, I'm treating the symptoms as the cause. But FA flips that script. It says, no, these symptoms are just messengers, telling us about the invisible thing underneath.
That's it, exactly. And this is why the math behind FA is so clever. It engages in what we call variance partitioning. Its primary job is to isolate the signal from the noise.
Okay.
It divides the total variability of every single observed variable into two big components. The first one is the common variance, which analysts often call the communality.
Communality.
This is the part of the variance that is shared with all the other variables in the set, and crucially, it's the part that is attributable to that latent factor. That is the signal we are trying to measure.
Okay, so that's the good stuff. What's the other part?
The second component is the unique variance. And this is everything else. It includes specific systematic variance that's unique to that single item. The unique meaning of fatigue versus sadness. And most importantly, it includes all the random error variance.
Just measurement noise.
Just junk, simple measurement noise. The genius of factor analysis is that its statistical model works exclusively to model only the common variance. It explicitly ignores the unique and error variance, which makes it the right tool for isolating true, clean, latent constructs.
So if FA is this exercise in filtering out the noise, then PCA is basically the opposite.
Absolutely. Principal component analysis is not a latent variable model at all. It's fundamentally a mathematical data reduction technique. It's not based on any causal hypothesis.
So what's it doing with the variance?
It seeks to generate linear combinations of the original variables, the principal components, that explain the maximum amount of total variance. And when we say total, we mean common variance plus unique variance plus all the error variance.
So PCA is like dumping all the ingredients in the pantry into one giant pot and calling the mixture a summary of the pantry.
That is a perfect analogy.
While FA is over here trying to isolate the pure vanilla extract.
That's it, exactly. PCA treats its components as just aggregate summaries or indices of the data, not as underlying causes. Now, it's computationally simple, and, it often produces similar results to FA if you have a really high-quality data set.
But theoretically?
But theoretically, it's deficient from measurement theory. Because PCA capitalizes on that error variance, it tends to inflate the factor loadings. It summarizes everything, the signal and the noise, which makes it unreliable if your main goal is to identify a pure, error-free, latent structure you can use to diagnose or predict behavior.
Okay, so that's clear. If I'm trying to confirm a theory about human nature, I need FA. If I just want to make my giant data set smaller for easier processing, maybe PCA is okay.
That's a good rule of thumb.
But now we know we need FA for theory. And that theory-building process brings us to the two distinct modes of using factor analysis, which kind of mirror the two major phases of the scientific method itself.
Right. Discovery and then testing.
Let's start with that discovery phase, exploratory factor analysis, or EFA.
EFA is the inductive data-driven approach. It's the tool for scientific exploration. It's what you use when you have minimal a priori theory.
So you're just starting out.
We're just starting out. Imagine a team developing a brand new scale for a concept that has never been measured before, like, say, digital overload stress. They need the data itself to reveal what the underlying structure even looks like.
So they don't have a map. They're asking the data to draw one.
Exactly. In EFA, the researcher gives the data maximum freedom. The factor loading matrix is considered fully saturated, which just means that every single observed item is allowed to potentially load on every single factor that gets extracted.
No constraints.
No constraints. The objective is just to identify the minimum necessary number of constructs you need to explain the observed correlations, and then to map out the nature of those constructs.
And this is the phase where analysts grapple with all those confusing statistical rules for deciding how many factors to keep, right? I remember reading about things like the Kaiser's criterion keep factors with eigenvalues greater than 1.
Right.
Or looking at that famous bend in the scree plot.
Right.
But the sources note that these simple rules are increasingly seen as, well, insufficient.
Insufficient is a kind way to put it. While those older heuristics are still taught, they are really prone to significant over-extraction.
Meaning they find too many factors.
Way too many. They suggest far more factors than actually exist in the data. So modern methodology now strongly favors techniques that rely on random data comparison. The most notable one is parallel analysis.
How does that work?
It's pretty clever. Parallel analysis compares the actual eigenvalues from your real data to eigenvalues generated from random simulated data of the same size. You only keep the factors from your data whose eigenvalues exceed those that were produced by pure chance.
Ah, so it sets a much higher bar.
A much more robust, objective bar. It's a way to move the field away from these subjective visual interpretations, like just squinting at a scree plot.
Okay, so EFA is for structure generation. But once that structure is proposed, we have to test it. And that's when we move to the rigorous deductive phase. Confirmatory factor analysis, or CFA.
CFA is deductive and strictly theory-driven. It is the gold standard for validation and scientific testing. In CFA, you don't ask the data what the structure is. You tell the data what the structure should be, and then ask if it fits reality.
So you come up with a very specific hypothesis.
A very specific, pre-specified model based on established theory or maybe a successful EFA.
And what does that look like in the analysis?
It means you postulate that, say, item 1 and item 2 measure factor A, and item 3 and item 4 measure factor B, and then you deliberately restrict all the other non-theoretical loadings to 0.
So you're locking it down.
You're locking it down. This constraint is critical. You are testing a rigid theoretical structure against the empirical reality of the data. And this is what we use for rigorously testing competing models. For example, does our new survey for burnout fit a 3-factor structure of exhaustion, cynicism, and inefficiency better than a simple single-factor structure?
And the answer isn't a yes or no.
No, the evaluation is entirely based on these complex goodness of fit indices, things like the comparative fit index, CFI, and the root mean square error of approximation, RMSEA. It's this disciplined approach that makes CFA mandatory for validating established psychological, health, and sociological instruments all over the world.
So we go from this open-ended exploratory discovery to rigid structure testing. But no matter how we arrive at the factors, we immediately run into what might be the most subjective and potentially biasing step in the entire process: rotation.
This is where things get really tricky.
This is the part of the math that truly startles me. The sources state that factors are mathematically indeterminate, that there are an infinite number of orientations of the axes, the factors, that mathematically explain the data equally well. That feels like a contradiction of scientific objectivity. Infinite valid solutions.
It is the mathematical reality of working in multidimensional space. I mean, think of it like looking at a constellation in the night sky. The stars are fixed, they're in a certain position, but how you draw the lines between them, how you rotate your view, changes the picture dramatically. Is it a bear? Is it a dipper?
It's the same stars.
It's the same stars. Rotation is a process where the researcher decides where the axis should point to make the factors interpretable. You're aiming for something called simple structure, where each item loads highly on only one factor, which makes the factor's meaning much clearer.
And the choice of rotation is where the analyst's theoretical bias can just be baked right into the output.
Absolutely. It dictates the entire relationship between the factors. We categorize rotations into 2 major philosophical types. First, you have the more mathematically tidy approach, orthogonal rotation, with Varimax being the classic example.
Orthogonal means perpendicular.
Perpendicular. This method forces the factors to be uncorrelated. Geometrically, it ensures the factor axes remain at a 90-degree angle to each other. Now, this yields a very clean, tidy mathematical separation. It tells the world factor A is totally separate from factor B, but it is often theoretically indefensible in the social sciences. I mean, constructs like impulsivity and risk-taking or verbal ability and spatial reasoning, they rarely exist in a truly uncorrelated vacuum.
They overlap.
They overlap. Forcing that tidy separation using orthogonal rotation, especially when your theory suggests they should overlap, can actually distort the empirical reality of the data. You're simplifying complexity to the point of falsehood.
That sounds like you're enforcing an artificial reality on the data. And that's why the alternative, oblique rotation, using methods like Promax or direct oblimin, is so often preferred in fields dealing with complex human traits.
Oblique rotation is the more realistic approach. It allows the axis to rotate freely, which permits correlations between the factors. It acknowledges that human traits are almost always interconnected.
So if you find a correlation between anxiety and depression in your data,
Oblique rotation models that correlation explicitly, while orthogonal rotation just sweeps it under the rug.
and this choice has methodological consequences for what you see in the output.
For sure. Oblique rotation produces 2 distinct matrices, which you need because the factors are now related. You get the pattern matrix, which shows the unique, direct effect of the factor on the item, essentially controlling for the other factors, and you get the structure matrix, which shows the simple correlation between the item and the factor.
That sounds more complicated to interpret.
It is harder to interpret, but that complexity is necessary to accurately reflect the interconnected nature of the constructs you're studying. Direct oblimin is often the method of choice when you're dealing with psychological variables that are known to overlap significantly.
So we have this profound ambiguity right at the heart of the tool. 2 analysts, using the exact same data, can choose different rotations, leading one to conclude that, say, creativity and intelligence are separate entities.
And the other concludes they're linked.
And both are mathematically defensible descriptors of the covariance matrix, but they lead to totally opposing theoretical conclusions. The math is objective, but the interpretation is fundamentally subjective.
That's the core tension of the method.
Okay, we've established that factor analysis is this powerful tool built on subjective choices. But we need to spend some time acknowledging its staggering utility. I mean, it solved problems that seemed impossible to tackle, giving scientists the language and the metrics they needed to advance entire fields. Let's look at its core strengths, starting with its ability to simplify utter complexity.
Right, the strength of parsimony. It's fundamental to good science. If you can explain 50 things with just 5 concepts, those 5 concepts are far more valuable. And as we noted, social reality is messy.
Let's go back to that example of urban poverty.
Okay. A city planning agency might have dozens of variables. Average income, unemployment rate, housing density, distance to public transit, violent crime frequency, number of food deserts, educational attainment, broadband internet.
You could easily hit 50 variables.
Easily. And if you try to analyze all 50 of those in a standard model, the results are worthless because of multicollinearity.
Meaning everything is correlated with everything else.
Exactly. The variables are so highly correlated that their individual effects can't be statistically distinguished from one another. It's just a big statistical traffic jam.
A data traffic jam. I like that.
Right. Factor analysis solves this dimensionality reduction problem elegantly. It takes those 50 noisy, overlapping variables, and it reveals their underlying structure, that they actually cluster into maybe 4 or 5 robust, latent factors. Infrastructure quality, social cohesion, economic opportunity, and maybe environmental risk.
And then the researcher doesn't use the 50 variables anymore.
No, they calculate 4 distilled factor scores. And this process isn't just about making the data smaller, it's about extracting the pure, concentrated signal from the noise. It leads to simpler, more powerful, and far more robust models that allow city planners or sociologists to distinguish real effects instead of just chasing 50 overlapping shadows.
And the second indispensable strength is its role in proving that the measures we create actually work. It's the empirical engine behind construct validity.
Factor analysis is the empirical gatekeeper. It provides the statistical evidence for whether a test truly measures what it claims to measure. And we check for 2 things.
Okay.
First, convergent validity. This means items that are intended to measure the same construct should cluster together strongly. If you have 5 items intended to measure hostility, they should all load highly on the same factor, say above 0.40 or 0.50, which demonstrates they converge on that single latent concept.
And the second?
Second, discriminant validity. The constructs themselves must be empirically distinguishable, so FA tests whether items designed to measure anxiety separate cleanly from items designed to measure depression, even though anxiety and depression are highly comorbid and share symptoms like sleep issues.
Which they do.
Which they do. Factor analysis was crucial in showing that the core symptoms of anxiety-like worry load on one factor, while the core symptoms of depression-like anhedonia load on a distinct, separate factor. This justifies their treatment as 2 separate diagnostic entities. It systematically maps concepts onto data, allowing us to scientifically justify why 2 things should be treated as distinct.
And finally, you touched on the issue of measurement error earlier, but the way FA handles error is often overlooked as a strength.
It's arguably its most practical advantage. Simple methods, like just averaging or summing up item scores on a quiz, assume every item is an equally good, perfect measure of the underlying construct.
Which is never true.
It's fundamentally untrue. Factor analysis is smart enough to know that some questions are better than others. It implicitly weights items based on their actual correlation with the latent construct. A poorly phrased, ambiguous question, a poor quality item, will have a low factor loading.
So it contributes less to the final score.
Exactly. It contributes minimally to the final factor score. By minimizing the influence of noise and poor measurement quality, FA generates measures that are far more reliable and valid than any crude summation method could ever hope to be.
That's a serious step up in rigor. Now let's look at 3 areas where factor analysis didn't just analyze data, it fundamentally defined the field. Let's start with the chaos of personality psychology.
Oh, it was a mess.
Before factor analysis entered the scene, personality psychology was, as the sources describe it, a Tower of Babel. What did that fragmentation look like?
It was an incredible mess of redundancy. I mean, the early field was operating under the lexical hypothesis.
The idea being.
The idea that all truly important individual differences must be encoded in the language we use to describe each other, which sounds reasonable, right? But when Allport and Odbert undertook the massive task of compiling English adjectives describing personality back in 1936, they ended up with a list of over 4,000 distinct terms.
4,000.
4,000. And you had hundreds of overlapping words like chatty, garrulous, talkative, and loquacious. Scientists simply couldn't communicate or replicate findings globally because everyone was using their own pet list of traits.
So someone had to clean that up.
Raymond Cattell used early rudimentary factor analysis to try and tame this chaos. He successfully reduced the list to about 171 items and then extracted 16 factors, his famous 16PF. But even 16 factors was still too complex to be reliably replicated across different labs and cultures.
So how did factor analysis finally get us to a consensus?
Well, it took decades and the refinement of the technique. Researchers like Tupes, Kristall, and later Goldberg applied more sophisticated and robust factor analysis methods to that same massive pool of adjectives. And what emerged consistently across study after study were 5 broad dimensions that accounted for the bulk of the variance in human personality.
The big 5.
The dimensions we now universally accept: openness, conscientiousness, extroversion, agreeableness, and neuroticism.
Ocean. And this was FA's great theoretical achievement.
It absolutely was. It forced a consensus. It demonstrated empirically that traits that appear distinct, like being talkative, assertive, and energetic, are not separate entities, but are all manifestations or reflections of a single latent variable: extroversion. This unified taxonomy standardized measurement, allowing personality psychologists to finally build consistent predictive models that link personality profiles to real-world outcomes, whether it's academic success, occupational fit, or relationship stability.
Okay, moving to sociology. The challenge of measuring class or status is equally abstract. How do you aggregate income, education, and occupational prestige into one meaningful number that truly captures a person's social standing?
It's impossible to use any single variable, right? A high-income high school dropout and a low-income PhD academic occupy really different social spaces, yet neither extreme is captured by just income or just education.
They're different things.
Right. And sociologists immediately realize that these variables are highly correlated because they share a common underlying factor: access to capital, social standing, that kind of thing.
So FA was the tool to combine them.
It became the mechanism for combining these disparate indicators into a single, continuous, defensible measure of socioeconomic status, or SES. By using FA, researchers are not just adding up numbers, they are finding the linear combination of those variables that best explains their shared variance.
And this is used everywhere, including in international policy.
Oh, absolutely. The International PFAS Assessment, which compares educational outcomes across industrialized nations, relies heavily on this approach. They use principal component analysis, which is functional for this kind of index creation goal, to create the Index of Economic, Social, and Cultural Status, ESCS.
And what goes into that?
It combines parental education levels, parental occupational status using complex metrics of job prestige, and critically specific home possession.
Home possessions like what?
Things like books, computers, a desk, and this is where the data-driven weighting becomes paramount. A simple score might treat owning a computer the same as having a master's degree, but the factor analysis dynamically weights the indicators based on their empirical load.
So it figures out what's most important.
Exactly. In many modern PISA datasets, the variable number of books in the home might load more heavily on the ESCS factor than a raw income measure.
Why would that be?
Because the presence of books reflects not just wealth, but cultural capital, a parental value of learning, an intellectual home environment, all of which are potentially better predictors of educational success than just the raw paycheck. FA ensures the measure is sensitive to the actual social dynamics at play.
Okay, so we saved the most defining case study for last, because it links directly to our biggest critiques later. Factor analysis was not created for personality or sociology. It was created in 1904 by Charles Spearman, specifically to measure intellect.
That's right. Spearman noticed what he called the positive manifold. He looked at children's test scores, and he saw that their grades in math were positively correlated with their grades in Latin, which were correlated with their grades in classics, and so on.
So if you were good at one thing, you tended to be good at the others.
Right. They were distinct subjects, yet success in one tended to predict success in the others. And this observation suggested to him that all intellectual tasks must share something in common.
So he invented a tool to find that something.
He invented a tool to find it. When Spearman applied his new factor analysis method to the correlation matrix of these different scores, it forcefully extracted a single dominant factor that accounted for the majority of the shared variance across all the intellectual tests. He named this factor D dollars, or general intelligence.
This was revolutionary.
Yeah.
It instantly validated the idea that intelligence wasn't just a random collection of skills like being good at math and good at music, but rather one fundamental underlying mental energy.
Exactly. It provided the statistical proof for the concept of IQ as a unified measure. The implication was clear. D dollars is the central engine that influences everything you do cognitively. Now, later models, like Thurstone's, argued for multiple specific factors like verbal comprehension, spatial reasoning, memory.
A more fragmented view.
A more fragmented view. But here's the kicker. When researchers applied second-order factor analysis, where they took those specific factors and factored them, those separate factors consistently correlated with each other and loaded onto a single higher-order factor.
Which was the original dollar.
Original dollars. This consistent finding across a century of research demonstrating that different cognitive abilities share a common source of variance has made Differ dollar the single most replicated finding in all of psychology. And it perfectly illustrates FA's power to define what we think of as fundamental human constants.
So factor analysis is powerful enough to give us the structure of personality and the very concept of general intelligence. It reduces complexity, confirms validity, and defines our reality. But the power of this tool is exactly why the critique has to be equally powerful.
It has to be.
The sources make it clear. FA is not a neutral mirror reflecting truth. It is a highly contingent model based on the analyst's subjective choices. It is only as good as the decisions made by the person running the analysis.
That is the essential message. The fact that the method requires choices about rotation, extraction method, labeling. It means that the objective mathematical result is profoundly shaped by subjective judgment. And we have to start with the most basic failure mode, like garbage in, garbage out, G.I. Joe principle.
Right.
Factor analysis is a magnificent organizer, but it cannot organize what is not there. If the input data is flawed, either incomplete, biased, or just poor quality, the factor structure that emerges will be equally flawed. But because it has that veneer of mathematical rigor, the results can be incredibly misleading and authoritative.
The most common failure seems to be tied to what we decide to measure in the first place, the item selection bias.
Oh, this is pervasive. Imagine a researcher wants to study effective leadership. They develop a survey, but perhaps unconsciously or just due to time constraints, they only include items related to behaviors like dominance, assertiveness, and control. When they run the factor analysis, they will find a perfectly coherent, highly robust factor. They will confidently publish their findings, defining effective leadership based on their factor structure.
But the factor isn't really leadership.
It is not leadership, it is only dominance and control. The analysis could not possibly identify crucial components of effective leadership, like empathy, vision setting, or team building, because those items were never sampled in the initial survey. The derived factor structure is entirely an artifact of the items the researcher chose to include, confirming a pre-selection bias and artificially narrowing the scope of the concept.
You're saying the math doesn't correct for conceptual blindness, it enshrines it.
It enshrines it, exactly. And GAGO extends to the respondents, too. I mean, think about the impact of careless responding in those large, monotonous online surveys.
Where people just get bored and click through.
Exactly. If participants get bored or distracted and start straightlining, answering identically down a column, selecting 7 strongly agree for everything, this creates massive artificial correlations across every single item.
The analysis sees that as a pattern.
Factor analysis dutifully interprets this induced noise as a strong, coherent structure. The researcher then claims they have discovered a unified general factor driving all the responses. They might even name it something grand like general life satisfaction. In reality, they have only measured respondent fatigue and measurement error. The statistical coherence is a mirage created by flawed input.
The next profound challenge comes after the math is done. We've extracted the factors, but we still have to give them names, which brings us right back to the indeterminacy of rotation. If two mathematically valid solutions can lead to contradictory theories, how can we trust the names we give the factors?
This is the critical problem, because the choice between orthogonal uncorrelated and oblique correlated rotation is subjective. The analyst gets to choose the theoretical reality they want to promote. A researcher who favors a multifaceted view of cognition might choose orthogonal rotation, mathematically separating verbal ability and spatial ability.
While
Another researcher trying to prove a unified theory might choose oblique rotation, showing that they are highly related. Both are just mathematical lenses, but they lead to fiercely defended, contradictory theoretical camps.
and then you have to name the result.
Then you hit the naming fallacy. This is where statistical description is swapped for causal or theoretical meaning. Political scientist R.J. Rummel gave a classic warning about this.
What was Rummel's warning?
He described a study where a factor was extracted that loaded highly on variables like military coups, political assassinations, and purges. Descriptively, you could name this factor political instability. That's a fair summary of the data.
Seems reasonable.
But if you name that factor modernization pains, you have just done something fundamentally dangerous. You have taken a descriptive statistic and baked a specific, unproven causal theory that political violence is a necessary byproduct of modernization right into the label.
And everyone who reads that study will just assume the math proved the theory.
Exactly. The objective statistical result becomes a Trojan horse for theoretical bias, potentially skewing policy and future research that relies on this authoritative-sounding measure.
That power to mislead seems to drive the constant creation of new, often unnecessary concepts in social science.
It leads directly to the trap of bloated specific factors. This is the methodological engine behind what's called the narcissism of small differences. If I am studying neuroticism and I include 10 survey items that are semantically redundant, like I feel anxious, I worry a lot, I feel tense, I get stressed easily,
They all mean basically the same thing.
they're designed to correlate intensely with each other. Factor analysis, being mathematically literal, will pull those highly specific, highly correlated items out as their own distinct factor. A researcher might then name this new factor acute situational tension and claim they have discovered a new, essential psychological trait.
When really it's just an artifact of their wording.
It's an artifact. They've simply created it by using redundant phrasing. And this proliferation of redundant, highly specific factors leads to diagnostic inflation, fragmenting our understanding of personality and psychopathology into dozens of overlapping, slightly different concepts.
This inherent subjectivity leads us directly back to intelligence research. The most famous critique of factor analysis, and specifically of the concept of death, came from Stephen Jay Gould in his landmark work, The Mismeasure of Man. He took aim at what he called reification fallacy.
Right. Gould argued that early psychometricians committed the logical error of treating Dedaller's mathematical abstraction derived purely from correlations, as if it were a real, physical, immutable, biological entity in the head.
Like a cognitive muscle.
Like a cognitive muscle or an organ. His core warning was profound. Factor analysis is just a way of structuring and representing data. It is not a magical discovery tool that reveals the unchangeable structure of human biology.
So he was attacking the interpretation, not the math itself.
Exactly. He essentially said, look at the math, not the myth. He pointed out that the existence of a dominant first factor, $2, was not a guaranteed finding of nature, but rather a predictable result of the mathematical decision to use principal component extraction, which is designed to maximize the variance explained by the first component you pull out.
So if you set the math up to find one big thing, you will find one big thing, regardless of whether that big thing is biologically real.
Precisely. He used geometric arguments to demonstrate that if you simply rotated the factor axis using methods designed to disperse the variance rather than concentrate it, you could explain the test scores equally well using multiple, largely independent factors.
Like verbal skills, spatial skills.
Verbal skills, spatial skills, numerical skills, without needing a single monolithic dollar.
So what was his conclusion about why they did that?
Gould argued that the insistence on maximizing D-dollars by early psychometricians was driven less by a desire to discover biological truth and more by a sociopolitical preference, the desire to rank and sort people onto a single, continuous hierarchical scale. The factor describes correlations, yes, but its interpretation as a fixed biological destiny was the reification fallacy in action. And that critique remains the most powerful warning in the social sciences about the dangers of treating statistical output as guaranteed truth.
Gould showed us the dangers of assuming statistical reality as biological reality. But there's another layer of assumption. Assuming a factor structure found in one place is universal. This exposes the deep-seated weird bias in much of psychological science.
Right, studies that overwhelmingly use participants who are Western, educated, industrialized, rich, and democratic.
So we're really just studying one type of person.
We are. And the problem is that if the big five personality factors are truly the universal architecture of human temperament, they should emerge consistently everywhere. But our factor analytic structures are often fragile cultural products.
And there's a key study that showed this.
A powerful demonstration came from a 2013 study that administered translated Big Five inventories to the Tsimane, a forager horticulturalist society living in the remote Bolivian Amazon. The researchers had excellent data and methods, but when they ran the factor analysis,
What happened?
the data simply would not conform to the established five-factor structure of ocean. It was a methodological failure for the universalist hypothesis. The model just didn't fit.
So what structure did the data reveal about the Tsimane?
The analysis suggested a radically simpler structure, a Big Two personality framework centered on pro-sociality, behaviors beneficial to the community, and industriousness, hard work and energy. The subtle differentiations we find in weird populations just didn't exist statistically among the Tsimane.
And what's the implication of that? Why would their personality structure be so different?
It's fascinating. In industrialized weird societies, our work life, which relates to conscientiousness, is often very separate from our social life, which relates to extroversion. These traits are statistically distinct for us. But in a subsistence society like the Tsimane, work is inherently social.
Group hunting, communal farming.
Exactly, shared resource management. These things are inseparable. So the statistical models reflected their reality. Traits like hard work and social engagement merge into a single, cohesive industriousness factor because they are functionally merged in daily life. Factor structures, therefore, are often cultural byproducts, not immutable biological universals waiting to be discovered.
This cultural limitation, combined with the naming fallacy, highlights two specific logical errors that factor analysis both creates and, thankfully, is uniquely suited to debunk: the jingle and jangle fallacies.
These fallacies are all about errors in conceptual labeling. They illustrate confusion over redundancy and separation. Let's start with the jangle fallacy. This is when researchers assign different names to the same thing. It's rife in fields where people try to rebrand old concepts for novelty or to get grant funding.
And you have an example.
The classic modern example is the psychological construct of grit, which was defined as passion and perseverance for long-term goals. It became hugely popular in education and organizational psychology.
I've heard of it.
Right. But rigorous factor analytic studies were eventually conducted to test the grit scale against established personality measures, and the results were crystal clear. The grit scale items loaded almost perfectly and almost exclusively onto the existing Big Five factor of conscientiousness.
So factor analysis essentially stripped away the marketing and revealed the core psychological structure underneath.
Exactly. It exposed grit as fundamentally conscientiousness repackaged with a compelling, marketable new name. FA is a powerful statistical solvent for dissolving redundant concepts and preventing the fracturing of knowledge.
And the opposite side of that coin is the jingle fallacy.
The jingle fallacy.
Yeah.
Using the same name to refer to different things. This is where FA forces necessary precision. Consider the concept of empathy.
Yeah.
When people use that word, they often collapse several distinct psychological processes into one label. But factor analysis, when applied rigorously to empathy measures, frequently reveals that empathy splits into two, sometimes three, distinct factors.
All right.
Cognitive empathy, which is the ability to intellectually understand what another person is feeling, to take their perspective, and affective empathy, which is the capacity to actually feel the corresponding emotion and response.
And separating those is important.
It's crucial because these factors correlate differently with other variables. For instance, individuals diagnosed with psychopathy often score high on cognitive empathy. They understand exactly what manipulation causes pain, but they score extremely low on affective empathy. Factor analysis forces researchers to acknowledge that the single label empathy is insufficient, compelling them to treat and measure these two constructs separately, leading to much more accurate theoretical and diagnostic models.
Okay, so the journey of factor analysis is one of groundbreaking utility, followed by this intense, necessary self-criticism. Since the Gouldian critique and the exposure of cultural bias, modern analysts have had to dramatically raise the bar for rigor. So what are the modern best practices designed to manage these inherent risks and prevent subjective choices from masquerading as objective truth?
Well, the days of simply accepting the defaults in statistical software, running a principal component analysis with a Kaiser criterion for extraction and a Verimax rotation, those days are over for serious researchers.
Yeah.
Modern practice demands justification and rigor at every single step. Take sample size. Researchers are moving away from old, simplistic rules of thumb, like you need 10 participants per item.
Because that's too simple.
It ignores the complexity of the actual model. Instead, best practices now involve using sophisticated techniques, like Monte Carlo simulations, to justify the required sample size based on the specific complexity, the anticipated strength of factor loadings, and the number of factors in their theoretical model. This ensures that the results are stable and replicable, not just artifacts of a small sample.
And what about the data itself? Most social science data comes from Likert scales, those 1 to 5 or 1 to 7 agreement scales. You can't just treat those ordinal responses like continuous numbers, right? That violates basic assumptions.
That is a fundamental technical error that plagued decades of research. Standard Pearson correlations assume continuity, which is inappropriate for ordered categorical data like Likert scales. Modern best practices mandate that researchers use polychoric correlations.
Which do what?
They estimate the relationship between the latent continuous variables that are underlying the discrete Likert responses, and they use specialized estimation methods like WLSMV instead of standard maximum likelihood, specifically to model the ordinal nature of the data accurately and prevent biased results. This is, it's non-negotiable for high-quality work today.
This precision becomes absolutely critical when you want to compare groups. Say, comparing the job satisfaction factor scores between employees in Germany and Japan, or between male and female executives. You can't just compare them unless you know the factors mean the same thing in both groups.
Exactly. And this leads to the most important checkpoint in comparative research: testing, measurement, and variance. Before any meaningful comparison of factor scores can be valid, researchers must perform a multi-group confirmatory factor analysis, MGCFA.
To prove what?
To prove that the items load on the factors in the exact same way for both groups being studied. For instance, if the item "I work hard" loads strongly on the conscientiousness factor for German workers but weakly for Japanese workers, then the factor itself means something different to each group.
The measurement isn't equivalent.
It's not equivalent. It's not invariant. And if invariance fails, you hit a methodological red light. Any subsequent comparison of mean factor scores is statistically invalid. It's meaningless.
And how do they handle that inescapable problem of rotation ambiguity, where two solutions can be mathematically sound but theoretically contradictory?
Well, analysts combat this inherent subjectivity by demanding factor stability. A robust research report will often test and report multiple rotational solutions, for instance, running both Verimax and Directed-Blumen, to confirm that the core factor structure persists regardless of the subjective rotational method chosen. This gives confidence that the structure is a robust feature of the data and not just an arbitrary artifact of the analyst's preference.
The sophistication of statistical methods is clearly increasing. But as the volume and type of data change, massive text corpora, social network connections, nonlinear streams, how is factor analysis integrating with the power of machine learning?
That's the frontier. Traditional factor analysis relies entirely on linear assumptions. It assumes a straight-line relationship between the latent factor and the observed item. But social reality is increasingly understood as nonlinear.
So we need new tools.
We need new tools. The future of dimensionality reduction involves integrating FA principles into machine learning techniques. Models like deep learning, specifically autoencoders, are essentially nonlinear generalizations of factor analysis.
How they work.
These models use multiple hidden layers to compress and then reconstruct complex data, be it massive text samples or social network graphs. They are highly effective at performing dimensionality reduction and feature extraction, much like FA, but they can capture incredibly complex, nonlinear latent features that traditional linear FA would simply miss entirely.
So we've made the math dramatically smarter to handle this new complexity. But are we still running into the same philosophical pitfalls that Charles Spearman and R.J. Rummel faced a century ago?
Unfortunately, yes. Despite the massive advancements in mathematical capability and complexity, the core challenge of interpretability remains unresolved.
The naming fallacy again.
It's the naming fallacy on steroids. When these complex, nonlinear machine learning models extract an opaque, latent feature, a compressed numerical vector from a social network, translating that mathematical feature into a meaningful linguistic concept that humans can use for policy or theory, well, it remains incredibly subjective and difficult. We are still grappling with the exact same risks of the naming fallacy and potential reification, just at a much higher technological scale, where the mathematical decisions are even harder to trace back to their source.
Okay, so factor analysis is truly a revolutionary tool. It forced necessary consensus in chaotic fields, giving us the unified theory of personality in the Big Five, establishing defensible metrics for social stratification like SES, and defining the most replicated concept in all of psychology, general intelligence, or dealers.
It is the primary method we use to validate our theories and reduce overwhelming complexity into interpretable, manageable signals. It has immense power. But the critical implication, driven home by the powerful critiques of Gold and the cross-cultural failure of the Semani study, is that this tool is not a direct lens aimed at some platonic truth. It is a highly contingent statistical model. The factors it extracts are entirely dependent on three things: the completeness of the data you put in, the specific culture and population you sampled, and the fundamental subjective mathematical decisions made by the analyst.
Rotation, extraction method, labeling.
All of it. Factor analysis does not magically discover reality. It structures our observation of it, and that requires intellectual humility and a constant awareness of its profound epistemological limits.
That is the crucial warning we leave you with. Since factor analysis structures so many of the metrics used to govern policy, education, and personal diagnoses, from school ratings to psychological reports, you should consider how many immutable truths or established facts you accept might actually be the mathematical result of a single subjective choice of rotation method, or the initial, flawed item selection of a researcher decades ago. What widely accepted measure in your own field might be a bloated specific factor, just waiting to be exposed by applying rigorous modern methodology. That structural ambiguity, that space between mathematical certainty and theoretical subjectivity, is what defines the modern social world.